Almost everything we do online is powered by this massive, totally invisible architecture. Today, we're digging into distributed systems. We're going to set up the fundamental game board that engineers use to make separate, fiercely independent computers act as one cohesive unit. It's an absolutely fascinating puzzle, so let's just dive right in.
Here's our roadmap for this explainer. We're going to cover the anatomy of these systems, the rules of the road, how to prepare for inevitable failures, upgrading our network links, and finally, my absolute favorite, the illusion of time.
All right, part 1, Anatomy of Distributed Systems. Let's set up the board.
So to really get this, we have to strip away the physical stuff, the wires, the routers, your home Wi-Fi, and just look at the bare fundamentals. At its core, a distributed system is just a bunch of independent processors, or nodes, and the communication links connecting them. Think of inter-process communication basically like sending physical mail. Every processor has an inbox and an outbox. Data gets bundled up into a message and tossed across a channel, and we actually categorize these messages by who's involved in the conversation. Unicast is just a simple one-to-one chat. Multicast? That's one node talking to a very specific group. Broadcast is exactly what it sounds like, one node grabbing a megaphone and shouting to literally everyone on the network. And Convergecast is basically the reverse of that. It's a whole group of nodes reporting back to one central boss.
Now, because all these processors are out there doing their own thing independently, we need a way to capture exactly what's going on across the entire network at any given split second. We call this a configuration or sometimes a state. Imagine zooming out into a sort of God mode global perspective and snapping a photograph of the entire system. That single picture captures the local state of every single process, whether it's crunching numbers, just waiting around, or completely finished, plus every single message currently in transit inside those channels. Just one tiny computational step by a single node shifts the whole system into a brand new configuration. String all those configurations together, and boom, you've got an execution. Basically a full-length movie of your system's behavior.
Moving on to part 2, the rules of the road, winning and losing.
So, the board is set up. We've got nodes, we've got messages, but what's the actual goal here? Well, every distributed algorithm has to balance two fundamental properties, safety and liveness. Safety properties basically guarantee that nothing bad happens. And here's the catch. If a safety property breaks, it happens at a very specific pinpoint moment in time, and you cannot fix it. Think of a bank account balance dropping below zero when it absolutely shouldn't. The damage is done. Liveness properties, on the flip side, guarantee that something good eventually happens. You actually can't break a liveness property at a specific moment, because there's always the chance it might be satisfied somewhere down the road. I love the traffic light analogy for this. Safety means the lights are never green in all directions at once, right? It prevents a catastrophic crash. Now, you could get perfect safety by just making every light red forever, but you'd get zero progress. And that's where liveness steps in. It guarantees that if you're stuck at a red light, it will eventually turn green, so traffic can actually move.
Oh, and this actually brings up a really fun but crucial language trap that catches engineers off guard all the time. There's this false friend translation between English and German technical terms. In English, when we say a liveness property guarantees a message will eventually be delivered, we mean certainty of outcome. It is 100% going to happen. But in German, the word eventuell just means possibility, like it might happen. In our distributed systems world, liveness means the event will absolutely occur, even if we are totally in the dark about exactly when that might be.
Which brings us to part 3, preparing for system failures, the obstacles.
Up to this point, we've been kind of pretending everything is perfect. But the harsh reality of computer networks is, well, it's total chaos. Algorithms absolutely require structured assumptions just to survive out there in the wild. Let's look at the ways a single node can stumble, because we have to build models assuming these faults will happen. First, the crash fault. Super straightforward. The processor just completely dies, lights out, never comes back. Then there's the omission fault. The processor is technically running fine, but due to network traffic or memory overload, it just randomly fails to send or receive messages. Then we've got crashes with recoveries. This is when a node dies, reboots, but wakes up with a terrible case of amnesia and loses all its temporary data. And of course, eavesdropping, where a node is secretly leaking private, sensitive data to the outside world. Now, these are all accidental or hardware-based faults.
We can design systems to recover from crashes and drop packets, but I want you to consider a much more terrifying scenario. What if it's not an accident? What if a node actively lies to you? Enter the Byzantine fault. This is hands down the most severe fault model in all of distributed systems. It's characterized by completely arbitrary behavior.
I mean, a Byzantine node can do whatever it wants. It can send fake data, it can give totally different answers to different peers, or just skip steps entirely. Whether it's a software bug, a malicious hacker, or a fully compromised server, our system has to assume an adversary is actively trying to take down the network. We call this the Byzantine generals problem, based on this old allegory where generals surrounding a city have to agree on a time to attack. But if even one traitorous general sends conflicting times, the whole coordination falls apart. The big takeaway here is that a robust system has to be mathematically bulletproof to tolerate F number of traitorous nodes out of N total generals, and still manage to reach a correct consensus.
All right, part 4, upgrading our network links. Let's build some better roads.
So, handling traitorous nodes is tough enough, right? But it's not just the computers themselves that fail. The actual conceptual roads connecting them can be incredibly flaky. Messages get dropped, duplicated, or show up totally out of order. So how do engineers fix this? They build what's essentially a theoretical upgrade path. We start at the very bottom with fair loss links. These are super unreliable, they drop messages left and right, but they are fair. The rule is, if you send a message an infinite number of times, it will be delivered an infinite number of times. It won't just black hole everything forever. So we take that baseline and use it to build stubborn links. A stubborn link just takes a message and relentlessly spams it, resending it continuously until it finally gets through. Then we wrap all of that in logic to filter out the duplicates, which gives us perfect links. A perfect link guarantees reliable one-time delivery with absolutely zero duplication and no phantom messages. Bam! We just turned a totally chaotic network into a flawless communication channel.
But a flawless channel isn't quite enough if there are still Byzantine traitors out there eavesdropping or injecting fake data. So we have to upgrade one last time to authenticated perfect links. We do this by injecting cryptographic primitives into the mix. We use hash functions, which act like unbreakable digital fingerprints for our data. We use message authentication codes, or MACs, which rely on shared secret keys to prove a message hasn't been tampered with in transit. We use digital signatures with asymmetric keys, so a sender can literally never deny that they sent a specific message. And finally, encryption to guarantee absolute data confidentiality. When you layer all these mathematical tools together, our links become virtually bulletproof.
Moving to part 5, the illusion of time. Coordinating all this chaos.
All right, so we've got our nodes, our links are secure, and we know the rules of the game. But now we hit the most mind-bending obstacle in all of distributed systems. There is no universal clock. Coordinating chaos without a shared clock is unbelievably hard. Let's compare the environments. In a synchronous model, everything is predictable. You've got strict speed limits for how long processors take to think, you have hard bounds on message delays, and perfectly synchronized hardware clocks ticking in unison. It's safe, it's clean, but the real world of the internet, that's an asynchronous model. In the real world, there are absolutely zero timing assumptions. Processors run at wildly different speeds, a message might take a millisecond or it might take a whole week to arrive, and there are no perfectly synced physical clocks. So how on earth do you know if event A happened before event B?
Well, the answer to that actually came from Leslie Lamport back in his legendary 1978 paper where he invented logical clocks. Instead of relying on physical timepieces like wristwatches, we just use numbers to track the happen-before relationship. Here's how it works. It's super elegant. First step, every single process just starts a local counter at 0. Simple. Step 2, every time a node does an internal action, it bumps its own counter up by 1. Step 3, when it sends a message out to another node, it grabs its current counter value and slaps it on as a timestamp. And step 4, here's where the magic happens. When a node receives that message, it looks at the timestamp, compares it to its own local clock, takes whichever number is higher, and adds 1. This incredibly simple logic guarantees that we can perfectly track cause and effect across a massive system without needing a single physical clock anywhere.
Now, pure asynchronous models are mathematically fascinating, sure, but they're a little too wild if we want to make real-world guarantees. So engineers usually rely on a hybrid model called partial synchrony. This assumes the system behaves asynchronously at first, meaning it's total chaos. Messages are heavily delayed, everything is totally unpredictable. But eventually, the system hits a tipping point called the Global Stabilization Time, or GST. After GST, the network calms down and conforms to fixed synchronous delay bounds. This actually mirrors the real world perfectly. Think about a network getting hammered by a denial-of-service attack. During the attack, it is pure chaotic asynchronous madness. But once the attack stops, meaning we hit that global stabilization time, the network breathes a sigh of relief and returns to predictable harmony.
And this ultimate puzzle of distributed systems leaves us with a really fascinating question. If we can't rely on physical clocks, and time itself is merely a logical illusion bounded by these stabilization events, how do we actually measure if our algorithm is any good? We can't exactly use a stopwatch, right? Instead, we have to look at message complexity, literally just the raw number of messages being sent back and forth. We measure communication size, the sheer volume of bits and bytes transmitted. And we measure communication steps, the sequential conversational back-and-forth rounds it takes to actually reach an agreement. In a distributed world, performance isn't about seconds ticking on a clock, it's about the efficiency of the conversation. But it does leave us with one final kind of mind-bending thought to chew on. As our networks keep growing, from local servers to global data centers, and eventually out to interplanetary systems, how are we going to agree on reality when the delay isn't just a few milliseconds, but literally minutes across the solar system? That is the endless, fascinating puzzle of distributed systems. Thanks for joining me for this explainer. Keep learning, and I'll catch you next time.